my pleasure to introduce today's speaker, Dr. Linlin Wang. Linlin got his Bachelor's of Science degree in physics from Nanjing University in China in 1997. And then he got his PhD in physics from University of Florida in 2004. After that, he was a postdoc at UIUC from 2004 to 2010. He then moved to Department of Energy Ames Lab in Ames, Iowa in 2010, and he is now an associate scientist. So today he will talk about tuning materials for topological quantum states. Please join me to welcome Dr. Wang.
Thank you. So can everybody in the back hear me? All right, good. So it's a great pleasure to be here. So I have a lot of great conversations with the faculty and the student. So, so the talk I'm going to give is about our recent work on finding and also, more importantly, how to tune material for the topological quantum state. So, and part of the motivation, so in the last decade, people have been finding this new perspective for the like a very old field. That's the like a solid state band structure, and we are probably very familiar. But for like maybe some undergraduate here, so if here will be like atomic structure, the crystal structure of silicon, then so in the reciprocal space, then it will be this kind of Brillouin zone. Of course, then there will be a highly degenerate point, K points on the boundary of the Brillouin zone, where you can get this band structure, right? You basically sometimes we call it spaghettis, right? So different bands. So this is the energy versus the K points. Of course, you can do this by according to energy, then you get a density state. You can do analysis projected on different atomic orbitals. You get the bonding, like chemical bonding of the inside silicon. Here, mostly like sp3 kind of hybridization. So this kind of picture and method have been working pretty well in the solid state physics in the past like almost 100 years. So, but however, there is an important ingredient that has been missing. That's the topology of this of the band structure. So from the basic science point of view, so we do have this kind of new understanding of band structure. And also on the applied side, this kind of new phenomenon can also has a great potential for new technology. For example, a new type of the symmetronics, also as well as like quantum computing. So in order to do that, we do need like material to realize that. So there have been a great effort across the world to searching for like new type of the quantum materials. So better yet, so I found this review article in the appeared in the end of last year. Can we do like quantum material on demand? That means we started with some material probably not have the quantum topological quantum state. Can we use the outside field, either like a strain with the pressure, also with like electric field or other type of field that can actually tune the material to have a new type of quantum topological quantum state. So here are the outline of the talk. So before I give you these 3 examples in my own research about finding and tuning materials, I will give first introduction to the topology of the band structure. We'll talk about how to define and also how to calculate the Z2 topological index. And we'll talk about the quantum spin Hall effect and as well as topological insulator. And in the last 2 or 3 years, there are new development about the nodal lines. These are the 3-dimensional nodal structure in band structure, and we found like also the Dirac and the Weyl points. So let's first start with, so when we talk about the topology, the first example people will always use is the quantum Hall effect. So here it will be the experimental setup. So for the undergraduate in the audience, so basically this experiment is you apply a current from top to bottom, and you also have this magnetic field point inward toward the screen, where then the electron will feel this Lorentz force. It will accumulate on the right side of the sample. Then this will make a kind of this make a potential across the sample in the y direction. So that will be measure that will give you the Hall resistivity. Now, if you increase the strength of the magnetic field, you find that past certain range, you will get these plateaus in the resistivity. Of course, when you inverse that, most people will call it Hall conductance. So that will be like an integer number times physical constant. And also, people have found that this Hall conductivity actually is really robust because it's topologically protected. So as later on has been found by Solos and his co-workers, so this phenomena is connected with topology or the quantum state. So in order to understand that, we'll first look at the normal insulators. So here is an example, the band structure, and we showed before, this will be like a field band, then there will be a conduction band, there was a direct band gap inside here, right? Then so the whole material will do like the mirroring, this will give you, there's no current, right? Except if there are some defects, then for the semiconductor, there will be depending on the carrier concentration. However, there's a different type of insulator. For example, for the quantum Hall excited, so because the magnetic field is so strong, and the electron will move in the cyclonic trace, so it moves like that. Then in the bulk, it will also form this kind of insulating kind of band structure. Instead of the normal band structure, here is the Landau levels. The degeneracy on the Landau levels will be proportional to the magnetic field. Then the interesting thing is, in contrast to the normal insulators, here you have this quantum, propagating edge state. So propagating on the edge. So that will give you this quantum Hall conductance. So these two different topologies. So people usually use orange and donut just to label them. So as we all know, that also here the topology protection comes from the gauge invariance. So that's basically the phase difference of the Weyl function. So, and we are quite familiar, this is the classical gauge transformation in solid state physics. So you start with the Weyl function in real space, and now you have a local phase field. So then there is a vector field, it will transform like that. So of course, the vector field itself is not physically measurable. And the measurable will be the magnetic field, it's the curl of the vector field. So in analogy, you can also do this in reciprocal space, where you work with the block Weyl functions, the U. And if you define the A as like, did by Michael Berry, it's called a Berry connection now. So if you define this quantity, then this quantity will, when there is a phase field in K space, it will transform similarly as in the real space for the vector field. Then now if you do the curl of the A here, then you get the Berry curvature. The Berry curvature will also be a physically measurable quantity. So the Berry curvature has been very useful, had to explain a lot of physical phenomena, for example, the polarization, the orbital momentum in materials, and also like the Linlin index in the 2D material too. So here I'm gonna focus on how to use Berry curvature to calculate topological index. So as the final note, so you can also do a direct analogy. So in the real space, the momentum operator is defined up to a function of the A vector. Also, that's the conjugated operator in the reciprocal space. So the position operator will define up to these Berry connections. So then we can also, talking about the topological index, this is well known in geometry, where you can, when you have this vector field in space, you can do there is a Gaussian Bonnet theorem, where you do the integral around a closed surface. You either get like this quantized values. You can also define them differently as the JNS. Basically, that's like how many handles of your object. So that's why the topology of donuts is the same as topology as a coffee mugs, right? Because it has only one handle. And in contrast, for the oranges, So there's only 0. So if you put 0 there, then of course chi will be 2, so then you recover the solid angle in the 3D space, right? So in analogy for the band topology, so of course we know the magnetic field. When we do the integral, there is no magnetic monopole yet. But however, in the band structure, you can do this integral with the Berry curvature. Then it gives you this Chern number. This also will be a topological index. So we talk about the quantum Hall effect. Now, how about the other topological state? So big breakthrough is in the late 80s. So when Haldane come out with the toy model, try to get the similar type kind of a quantum Hall effect, but without a net magnetic field. So this is what his model looked like. So he did a model with the it's called a 2D graphite. Of course, now we know it's called graphene, right? Since it it's foliated very nicely now. So in his model, so he added another term, so that will be the complex next nearest number hopping from that. So he called it a staggering B field. From that, so first thing is it will open up the gap. So without this term, you have form this Dirac cone where you have a Dirac point. So now with this gap opening, there's also that he found that because this next nearest complex hopping, there's an edge state propagating this way. Then later on in 2005, Ken and Mel also did a breakthrough work. So they found that actually you can replace this staggering B field with spin-optical coupling. So spin-optical coupling actually also reserve the time reversal symmetry. Basically, you have these 2 copies of Haldane model there. So now instead of 1 edge state, you have 2 edge states. So it's a pair. This pair, when the electron current is conducting in the same direction, but the spin actually propagating in the opposite direction. So that's the accumulation of spins. Okay. So this will be the type of the band structure here. So this will be formed like we call it a surface Dirac cone. So there will also be other type of bulk boundary correspondence. For example, in the 1D topological superconductor studied by like David Chen and also the quantum spin chain models. So so when they did this work, they tried to predict that graphene will be actually a 2D quantum spin Hall insulator, but for carbon, the spin coupling strength is so small, so it's not practically not measurable in experiment. So then Shuchun Zhang group, they came up with a quantum Weyl structure. So you have this telluride in between of these 2 layers of cadmium telluride. By varying the distance, by the thickness of this layer, then they have these different kind of band inversions. So from that, they predict that this is actually a quantum spin Hall effect. So then 1 year later, this is get confirmed, the other confirmation from experiment. So this will be a very clean sample where indeed you show the conductance and like twice of the fundamental constant, right? So later on, so next big development will be how do you extend it, this 2D quantum Hall effect, quantum Hall insulator to 3D. Then 3 different groups have been independently proposed their idea. So they all come to this, so where you need to look at the time reversal, invariant momentum in your space. And we just show in 2D, basically these time reversal invariant moments are like the boundaries in a brane zone. So for 2D, you only have the 4 trim points. So that's you just need to define 1 Z2 index. But for 3D, as you have 6 different planes, there's 8 trim point, but only if you do this calculation, you only need 4 indexes. So 1 will be the totally overall index defined as this. The other will be for each of the planes not passing through the gamma point. So the delta here will be kind of a quantity that actually measure this called the time reversal polarization. That depending on the gauge you choose. But however, if you choose 1 gauge, you do this product for this Z2 index. They are actually get invariant, right? So that's why these are defined as the topological index. And then later on for the like system where for the crystal structure where you don't have the inversion symmetry, this can be simplified by just look at the product of the parity eigenvalue of all the occupied states. It's like this. So another way, so then you ask the question, so what about the system where you don't have inversion symmetry? Then there's another equivalent way, another way to calculate Z2 index. So we should look at this, the expectation value of the position operators, right? We do that with these Wannier functions. So from that, you can look at the, like as a Wannier number for the called hybrid Wannier charge centers. So basically, the Wannier function is like a 3D FFT of your Bloch-Weyl function, but you can choose just to do it in 1D. So in that way, you do it in X direction, but you keep the Y direction as like still in the K-space. So now you look at like one plane of your 6 planes, right? So you want to know the topological index of that plane. So so then you have this Wannier charge centers. You look at the evolution of them. So basically, this gives you the Wannier number. So for example, this one is like that don't change. So the Wannier number will 0, and this one will just 1 pair DC. So the 1. Another one will be 2. So the Wannier number can definitely tell you the topological index. So you can define another one like the absolute value of them. This is multiplied by 2. Or actually, you can just take a direct expectation of the graph. Up to the half of the brane zone, you just took a line to see how many crosses you have. If you have an odd number of crosses, then you get Z2 next equal to 1. So that means that it's topologically non-trivial. Otherwise, it can be a trivial. So then experimentally, this have been several material have been proposed. So the best well-known will be like bismuth 2, selenide 3, where it shows very nicely this surface Dirac cone there comes from on the surface. So in the bulk, it's have a band gap. On the surface, you have these Dirac cones. And also importantly, so when you look at the cones, the surface structure, they have the spin and orbital spin and momentum coupling. So next, I'll give you how many, 20 minutes. Okay. So then the people will, in the last few years, ask the question. So now we know the topological insulator, right? It's protected by time reversal symmetry because you have this band inversion induced by spin orbital coupling in bismuth selenide. Then how about the other kind of band crossing in 3D band structure? There are quite a few. So for example, for some semimetals, you have these 2 band, parabolic band that actually cross. So these 2 points actually protected not by time reversal symmetry, but by like other space group symmetry. So this kind of inverted structure, they're not protected, not caused by spin orbital coupling, but will they be topologically also interesting, right? So all these kind of systems have been, because they are protected by certain symmetry, so they all call it like symmetry protected topological state. So a first example, I will say that will be like the 3D graphene network. So people have been talking about what's the like the 3D counterpart of the graphene, right? Graphene is 2D. You have the single Dirac, you have the Dirac cone. So I think the direct the counterpart will be this one. So this will be the graphene have this negative curvature that form like a regular lattice. If you look at the band structure, then you can see that along certain high symmetry direction, you have this kind of crossings. That's similar to the Dirac cone in 2D graphene. Of course, when you zoom in like around this region, around the R region, you see that these 2 points, they really form actually a kind of loop in the 3D reciprocal space. Of course, there are some energy dispersions depending on different case, right? So this will be the new kind of structure. You can define also a Z2 topological index, and I'll show you later. So this will Now, if you turn on the symmetric coupling, then the gap will be open up. So in certain high symmetry direction, that will be protected. That will form like a Dirac point. But of course, then you have other kind of distortion. You remove the inversion symmetry, then there will become like a topological insulator, but with a tiny gap. So that's kind of like the 2D version of this 3D version or 2D quantum spin Hall insulator in graphene, right? So of course, these kind of features are not only restricted to carbon materials. For example, for anti-peroxide, this material, they also have this type of the crossings around the endpoint. You can have this kind of 3D nodal loops. And also, so you can simulate it, you can define this topological index by the parity eigenvalues, because in this system, you also have the time reversal symmetry and well as the inversion symmetry. So one example for the Dirac semimetal would be the sodium-3 bismuth, right, where you have this nodal-line loop, then it's semi-optimal coupling will open up the gap, then only in certain direction. So this will be protected by the threefold symmetry. Then you have this Dirac point that's being confirmed in experiment. So experiment two, like uppers, is really good at look at this kind of surface structure features. So the next stuff will be the Weyl particles. The Weyl physics actually started much early on, right? It's right after Dirac proposed his equation, Weyl come up with his version of the equation. Basically, instead of 4x4 Dirac equation, you have 2. So they have different chiralities, right? And also early on, the Herring has noticed that actually in band structure you have this axial band crossing of 2 bands. From that, actually, it's a diabolic point. So it has so we call it Weyl point. So in reality, it's really hard to have because you need to tune 3 different parameters in order to get this axial band crossing. So in reality, how do you get the Weyl point? You start from something with a higher symmetry. Basically, you have either a nodal-line, semimetal, or Dirac semimetal. Then you break certain symmetries. For example, if you break the inversion symmetry, you have 4 of these Weyl points. They are a little bit off high symmetry direction. Then if you choose to break the time reversal symmetry, either by like a B field or like a magnetic moment of the material you have, then you have this Weyl point. So now the minimum number of them is 2. For the breakdown of inversion symmetry, due to the protection time reversal symmetry, you have a minimum of 4. Right. So in this talk, I'm gonna give you an example where you can actually start from something else. For example, if you have these 2 bands that are really close, aligned to each other, you have this atomic distortion breaking the inversion symmetry. You can also induce these Weyl points. Okay. So again, so as the last introduction to the Weyl point, so there are type 1 and type 2. Because in a solid system, you don't need to respect the Lorentz invariant, right? From that, then the cone itself can be tilted. So here we show that if your film entity here, then this Weyl point will be on the edge between the hole pocket and the electron pocket. So the first example will be type 1 will be thallium arsenic families. Then the type 2 will be tungsten telluride 2 families. For the Weyl point, because there are the singularity of the barrier curvatures, so that will project on the surface, then this will have connected by the film arcs. So before I give you an example, so let's just review quickly. So what's the spin-optical coupling? So the spin coupling, you can do the expansion for the Dirac equations. So the spin coupling term, actually, you can put them as they're proportional to the atomic numbers, like the z to the power of the fourth. So that means when you move down to the periodic table, so the heavy atoms will have much larger spin coupling, much larger, right? So there's also interesting interplay between the spin-optical coupling and the degeneracy. The symmetry we'll consider here will be time reversal symmetry and the inversion symmetry. So time reversal symmetry, we'll change both the orbital momentum and spin. So in that way, it preserves the time reversal symmetry. But if you do the inversion symmetry, then you will break the, you do the inversion symmetry, then only change the L, right? So because the electron is spin a half, so that means you always have this Kramer doublet like that, right? So now if we look at the band structures, so without spin optical coupling, the spin is independent from the optical momentum. You always have this spin degeneracy. So each band over here will be doubly degenerated. Now if you turn on the spin optical coupling, it's supposed to mix the spin up and spin down. But the band structure will depend on whether you have the inversion symmetry or not. If you still have the inversion symmetry, so you will leave some degenerate here for the gamma point, because that's just due to different atomic orbitals. Because you have this L and S, you have this J will be a good quantum number. Now here, each band is still doubly degenerated. However, if you don't have the inverse symmetry, then so the other band here away from the high symmetry point will also be lifted. So this kind of like a splitting, but without a magnetic field in this system without inverse symmetry. So it's called a dress horse or the rush ball if you have on the surface. Okay, so now I'm going to talk about my 3 examples. So the first one will be the ternary Zinto compound. So this compound is formed by 2 groups, the alkaline earth element, then there is the group 4 element. So they form this orthorhombic structure. The spec group is 62. So it basically have these glide planes on each of these x, y, z's. So along the y direction, if you put the plane on the atomic on here, then it will also become a mirror plane. So there's totally, if you count, there are 8 electrons per formula unit. So that's one of the Zinto compound, right? So now if you do like using DFT, your favorite DFT code, you calculate electronic band structure. So this is the density of state. So here, so that's the top of your valence band edge. Here will be a conduction band. So you see there will be the chemical bonding is mostly charge transfer. So most of the valence band come from the group 4. In this example will be germanium, and the conduction band come from the group 2 atoms, barium or calcium, right? If you look at the band structure, then here we show that it's a direct band gap at the gamma point. So about like 0.2 eV. So these ternary Zinto compound have been studied before in experiment for their thermoelectric properties. So they are all tend to be either like a narrow gap semiconductor or semimetal. So now if we move away from germanium, either to a silicon or to tin or lead, then the band structure, the dispersion features don't change much, but there is an important development around like the gamma point. So if you change to tin, then it doesn't change much, but for silicon and lead, there's something interesting here. So the lead is almost a semi-metal. So now we take a further look. So here is the result without and with spin optical coupling. So without spin optical coupling, it's have a direct band gap about 0.1 eV. Now if you turn on the spin optical coupling, then it will do this band inversion. So now, so the projection here will be like the red one will be projected on the lead p orbitals, and the green will be a projection on the barium 5d orbitals. So here you can see that there is a band inversion here. So that hints that this topological non-trivial, right, intrinsic state. So one way to tell is that we use one-year charge centers just to tell. So here will be without spin optical coupling. If you draw any line across the evolution of the one-year charge centers, you don't cross any lines. So now instead, if for the spin optical coupling, no, when you turn it on, then it's non-trivial. It's crossed just one time, right? So if you look at the Z2 index, it will be the 1, 0, 0, 0. So it's a strong topological index, strong topological insulators. So now when we look at the surface band structure, so this will be the spectral function of the semi-infinite slab. right? So this will be on a big view, so zoom out view. So you can see that there are the high intensity ones will be the surface band. So here, for example, this will be like your normal surface band because they come from the dangling bond. And there will be some features interesting here. So when you zoom in, here it shows that there's two surface bands. So this one comes from here, connecting from the conduction band all the way here to the valence band. There's another one coming from this side, connecting the conduction band to the valence band. They cross actually here, so that's a Dirac point. So that confirms that it's indeed like a surface Dirac point, that's gamma point. And this just shows that when you do the constant energy cut, so that will give you kind of like a 2D Fermi surface. It forms a ellipse surface.
Just clarify, what's the meaning of the color? The color goes from -2 for blue to 6 for red. What's the meaning?
Yeah, that's the spectral function of this. So basically, the higher means there's a higher density of states there. So basically, on the surface, besides the bulk states around here, that would be this one across to here. Then the actual high intensity will come from the surface band, and all these band gap region will be the negative ones. So now let's move to the other direction. So we move to silicon, right? The silicon have the very interesting features. Now, if we zoom in this region and show that it have this kind of two parabolic bands, they cross each other. So they have another type of band inversion, right? It's not caused by, so this calculation is without semi-optic coupling. So that means it's actually a band inversion not induced by semi-optic coupling, right? Just protected by symmetry. So these features, if you do this, if you look at the 3D, then it forms actually a ring structure, right? On the ky equal to 0, ky equal to 0 plane, so the xz plane. So these are protected by the mirror symmetry. So again, you can define a topological index for them because they have this both inversion symmetry and timer reverse symmetry. You can use these eigenvalues of occupied states. So you put them like that, then you will see that. So if you draw a line from x to z point across gamma, so inside this nodal structure, this topological non-trivial. So the v will be 1, the nu will be 1, and then outside this nodal structure, it will be trivial, right? So now we have to look at this again is do like a surface spectral function calculations. Now you can have this surface state actually kind of connecting these two node lines, the nodal structure there. So if you do the 3D, then it forms this kind of called the drum head, right? It's basically 2D Fermi surface, very interesting Fermi surface. Now, if you turn on the spin-optic coupling, so the spin-optic coupling will not change the band inversion, but it will create these small gaps, so it will open up for the full nodal lobes. Because this the rotational symmetry along the y direction is only twofold, so it does not protect the Dirac point. So it's now becoming a topological insulator. So we call it a nodal-line semimetal, like turned Ti. So you have a different state from the lead compound. The lead compound is induced by the band inversion is induced by semi-optic coupling, but here it is not. And you see here, so immediately, so this when the gap is opening, now you form this surface Dirac cone right there. Okay, so now here just to compare these two systems, right? Again, even though they have the band inversion from a different origin, but you still can come out with the same. You can use the same tight banding model. So it will be the K.P model to describe this. Of course, the coefficient will be different. That will give you will indicate the different origins of the band inversion. Okay, so now how about these two other compounds, the Germanium compound and the tin compound, right? We know that they have a direct band gap, but now, if this kind of nodal structure is protected by symmetry, in theory, you can easily do this, right? You just compress the whole system by uniform strain, right? So you get this crossing over there. So we checked, and indeed, they form this nicely nodal loop structure similar to the silicon compound. Right, so then if you turn on the spin-off coupling, similar story, then you open up the band gap here. The band gap is larger because germanium has the larger Z number, right? So again, it tends to a topological insulator here. So that means you can really use either like the pressure, or you can form if you can form some kind of alloy between these 4 different compounds. So this kind of like a schematic for this phase diagram, only theoretical, but right. So you use the pressure to compress silicon, then there will always be this nodal-line semimetal to the Ti state. On the other side, the lead compound will be a Ti state. But when you compress enough, then the band inversion will also happen. So that will tend to this nodal-line semimetal. So in between these 2 compounds, only with the pressure, then that can become the topological non-trivial state, the nodal-line semimetals, right? So that means you can use the alloying or pressure to tune the normal insulator, normal semiconductors to a topological non-trivial state. Okay, so now a second example would be the niobium nickel tellurium 2 compound. So here we show you first the structure. So if you look at the literature, there are the 2 reported structures. So one is spec group 53, the other one with spec group 28. So the difference between them is the inversion center. So, but on all other contexts, they are really similar. They're both like a layered stacking structure. So unlike the transition metal coordinate has been very popular now, right? It actually have another. There are 2 transition metals. So the nickel will be here, and in the center will be the niobium. So they kind of have this staggered layer structure, right? So to look at the difference between these 2 compounds, the structure, the difference is that you need to look at the symmetry. So along the spec group 53, they have actual like glider planes. Along the C, also the 2-fold rotational symmetry along A, and 2-fold Shigur axis along B, so that gives you the inversion center. But for the 28, there is no inversion center. If you compare the 2 structures as like a kind of atomic distortion that's corresponding to certain like optical phonon mode, you see that this basically mostly corresponds to the niobium in the center, niobium to tellurium stretching mode. So the stretching magnitude will be less than 0.1 angstrom. So that's probably like in the right range for the optical phonons. Now we look at like if you have these 2 different structures, one with inversion, one without, what's happen to the band structure? So we look at here. So first we look at without spin-off coupling, and so here you have a quite complicated band compared to the first example for the Zinto compound, right? So you have several. You have the continuous band gap here, but not so along gamma X, gamma Y, and Z. You do have these metallic band features. And now for the 28, similarly, but there are some the band degeneracy have been lifting because you remove the inversion center here. Also, the band order here also changes. So this will be the like kind of like electron band is move up here about these 2 like a whole electron whole band. So we'll do that. And now if you turn on the spin orbital coupling, because here you don't have inversion symmetry, so all these double degeneracy will be lifted, right? Like here. So compared to here. So with inversion symmetry, these all double degenerate here, they are removed, right? So if you take a further look, this will be a really interesting region. Because if you look over all these along the high symmetry directions, so they all have this, even though here I checked, these have a very small band gap. Okay, for all the other, it's obvious band gap. except for here. So that gives you a hint that probably there's some like a Weyl point probably happening there. So indeed, when we zoom in this region, so this is probably the band structure of gamma X direction. You can see here, this is the green dot will be the projection on the niobium on the DYZ orbitals. So these are actually pointing along the niobium to tellurium bonding direction. So you see there's some orbital character change here without for the structure with inversion symmetry. But here, without inversion symmetry, the double degeneracy is lifted, and also here these two bands come really close together, and also they have this band character change. So that means indeed really possible Weyl point. So we plot out the Fermi surface of this system here. As you can see, so here will be right at the Fermi levels. So this will be I think this will be the whole band. This will be the electron band. Now if you go down here, this part will be your whole band. This will be the electron band. So these two features will come very close, corresponding here. So the Weyl point will merge around the electron hole boundary. So then with the we construct after solving the band structure, we can also use the Wannier function to do the tight banding model. So the advantage of the tight banding model is you can do much faster calculations for the band structure. So you can just search through the whole brane zone, search to look at whether these two bands cross or not. So this is our result of the searching. So we found like these 4 different sets of crossings. So they are here. There's their energies, and here there's coordinations in the brane zone. So I will bring attention to the first set here. So this will be the set that actually have these electron hole boundaries, right? So when you zoom in, the gap region, as you show here, it indeed tends to 0. Also, you can just cut through in one particular direction. Then you can see that indeed they form these tilted Dirac cone features. And here will be the calculation to real Dirac conformation, calculate the barrier curvatures. So here are the barrier curvatures. So they are the vector field, and you can see that here will be the source for the barrier curvature. So +1, like then acting like a magnetic monopole. Then here will be the sink of this barrier curvature. Okay, so then for the surface spectral function, they are known. This Weyl point will form these Fermi arcs. So because they are very close in the K-space, so then we zoom in here and show that indeed this form this Fermi arcs here. And in the surface band structure, the spectral function here will be here is where the Weyl point located, right? So then this will be the surface state and connecting that. Okay. So how about the other set? So all these other 3 sets will be the type 1 Weyl points. So they're actually 2 of them also quite close to Fermi energy. All right. So then we also get a question asked frequently by other people. So how about if you change to different exchange correlation functions? What will happen? And we show that this kind of topological feature actually is really robust. So you can change to exchange correlation with van der Waals kind of interaction involved, and they will change your energy and some of the dispersion, but not these nodal features. So the nodal features is really robust. So that's one I think the advantages for this topological material. Okay, as the last example, I will talk about the platinum tin 4. So this part of the research actually is driven by our experimental collaborators. So, Professor Paul Canfield group first synthesized this compound. They measured like in 2004. They found that it has a large magnetic magnetoresistance. Then Adam Kaminsky group, they look at this band structure. So they noticed that there is a really unusual, like this surface band around the X point. So then they did a few cut, like in uppers. Then they noticed there are some nodal features there. So from here, this nodal feature, and you move along here, then this nodal feature will break into a pair. So this will have these kind of nodal features. So this actually kind of continuously. So it's really very kind of very unprecedented, I think, band structure. These have never been found before. So these Dirac points, instead of isolated points, are also not in, usually Dirac points should be protected by crystal symmetry, so they're usually at the high symmetry point. But these 2 points actually at the non-high symmetry point. They're quite close to X point, but not right at there. So then again, we did the surface band structure calculations. So actually, they agree pretty well with experiment. So see here the surface calculation, you get a very, like this will be the surface band and correspond to these 2 bands. And if you cut through this region, then you have these 2 Dirac cone formed here. So very good agreement, but we still do need more work to fully understand why this kind of structure will form in this compound. So in summary, I think I can show you 3 different examples where this interesting topological quantum state can be developed. The first example is for the Zinto compound, where we can use alloying to tune the symmetrical coupling strengths, and also with pressure for the strain to transform between these 2 different kinds of band inversions to move between the the topological state and the nodal-line semimetals. And in another example, the niobium nickel tellurium 2, so we use propose to use the optical phonons to break the inversion symmetry, and that will induce the Weyl points in the system. And the last example, so the Dirac nodal arcs is really kind of something special, and we are currently working on to try to fully understand it. All right, with that, I thank you for your attention.
Okay, question?
Oh, Brian?
Yeah. So in your first project with the Zental structures, you mentioned in the second one about the types of DFT that you were using and the fact that it was fairly robust. What do you see in that first one in terms of whether van der Waals corrections are needed or?
Yeah, good question. So in that study, we know that like DFT, the normal like GGA type thing, we will underestimate the band gap, right? So I show the band gap like only like 0.2 eV, right? But so we try to use like these with the hybrid exchange correlation functionals. That will correct for some material. But I think for this particular material, the correction can be actually overcorrect. Because we look at the Wang compound, you replace barium with magnesium. Magnesium, calcium, silicon. Experimentally found it like it's metallic transport behavior. But however, band structure, if you have this hybrid exchange correlation functional, and give you a gap like 0.5 eV. So I think for this particular case, I don't think the hybrid exchange correlation functional is really work well here. Yeah.
Can you comment on like how defect would play? Because you have ternary, right? Whenever you have ternary, then you could easily have the defect there. So how difficult, how easy to actually get into the control defect, and how defect would affect the computation?
Yeah. So we haven't looked at the defect, the native defect formation energy in this system yet, but for the property I'm talking about here, so actually the transport property of the topological insulator, right? They're always protected topologically, right? On the surface, so the band scattering from this usually defect, unless it's magnetic, right? Something. So usually they are well protected. So I would say from the transport perspective, the effect will be small. But of course, if the defect will actually give you some like change the film energy. If it become metallic, then that will totally change the story there, right?
I have a question.
Sure.
So according to your calculation as well as another experimental works, it appears like the topology insulators all have rather small band gaps.
Mm-hmm.
Is there a fundamental reason it has to be the case, or it just so happens that we are still not having a large gap insulator?
Good question. So for most of the topological insulator, right, I just showed that in this compound there are two types of band inversion. So for the nodal-line semimetals, it happens in in the silicon compound, the spin-orbit coupling can open up really small band gap, right? So probably the hope there is very very slim. So that would mean that we need to look at like the band inversion caused by the spin-orbit coupling. But in order for the spin-orbit coupling to work, so without spin-orbit, you should have these two bands really close with each other. So in the example on the lead compound, so without spin-orbit coupling, the band gap is only like 0.1 EV, right? So when you turn on spin-orbit coupling, that will indeed we will induce this band inversion. So in this kind of this phase diagram, however, if they're far apart with each other, then the spin-orbit coupling will not induce this band inversion. So the largest band gap until now, I think, is still the BaCaX2 selenide 3 families, about around 0.3 to 0.35 EV band gap.
So correct me if I'm wrong, but most of these calculations are all zero temperature. Is that correct?
Correct.
Right. So, but the experiments aren't at zero temperature. So how robust do you think the results that you're getting here at zero temperature are in comparison with the experiments? And how would you be able to include temperature if that's the problem in your analysis?
For the scattering part, so for the TI, when you have this surface metallic state and topologically protected, the phonon scattering, I think it will because it avoided this backward scattering, so I think it's still protected pretty well. But another aspect is for the phonon, like I talked in this material, you can use like optical phonon to induce Weyl point. But of course, in experiment, if you have the temperature, it will not break symmetry. So overall, the phonon ensemble will keep the inversion symmetry. But so that phonon effect will have the electron phonon coupling. That will broaden the band structure, right? So there are some earlier studies that say that kind of broadening and at certain compound can give you some band inversion features, right? But here we propose that, well, if you can, I will ask the help of Professor Zhao if you can do use the infrared pump, right, to excite the particular phonon mode. I think I have an example. So then it will, let's see, show you. Okay, oh, yeah. So here will be the phonon band structure for this material. So the red one highlighted is one of these infrared active mode. So if you excite this, then this will be the distortion it will cause. From that, then let's see that. Sorry, bear with me. Okay, so that one will give you also this type of Weyl features. Okay, so it's different from previous one because here you only you focus on you excited this particular mode. Then they give you actually 16 different Weyl points in 2 different sets. Yeah.
That's assuming sort of everything remains harmonic and you don't have phonon-phonon interactions.
Yeah,
That's everything